with a problem for which we have been doing the build up exercise for the last few lectures. So, that is the geometric set cover problem, and in particular we will assume that we have a configuration space where we have some kind of handle on the VC dimension. So, more generally, we have this range space S equal to x r, okay, and S has finite VC dimension. So, x is a set of n points, okay. And we want to choose subset, say r prime of R that covers all points of x, namely for all x in X there exists an R in R prime such that x belongs to R. So, it is no different from the set cover problem, except that now we are in a geometric domain, or we have a set system that has finite VC dimension. So, not absolutely general, we have some handle on the VC dimension, we are saying that the VC dimension is finite. Now, the general set cover problem is one of the most classic hard problems, right. It is an NP hard problem, and we have to live with some kind of approximation. And the classic greedy algorithm for the set cover gives you a log n approximation. Right. So, the question here is that, well, of course, we can use any kind of, because the generic set cover will also work here, okay. We can use the general set cover algorithm, say the greedy algorithm, to find a cover of size, let us say k times log of n, where k is the size of the optimum cover. What if we want to do better? Okay. So, the other thing I should point out is that in general, in the general framework, the set cover is a hard problem. It is provably a NP hard problem, but when I pose this problem in this context, okay, you have to actually formally show that this is also a hard problem. Okay. So, there are proofs, okay, for let us say some. So, so I can give you an example that if you consider the covering problem where I have a set of points, okay, and the ranges are circular disks, something like this. So, ranges are disks and points are points in the plane. So, there is a proof that this problem is a hard problem if you want to find the optimum size set cover. Okay. So, this problem is known to be impure, right, of finding optimum size. So, again the only thing that we can hope for is to, if we want to live in the polynomial time world, then we have to find a way to approximate this solution. Okay. And if we run the generic set cover algorithm, then it can be approximated within log n factor of the optimum size set cover. The question now is that given that we have this VC dimension constraint, can we do anything better? Right. So, can we improve upon the generic and it is also now known that log n factor approximation is kind of the best that one can do in polynomial time. I mean of course, modulo the fact whether if p is not equal to np. So, modulo p is not equal to np, that is the best that one can do. So, if we are hoping about something better than log n approximation, right, then clearly this problem is at least in the current state of knowledge, the problem will be easier than the generic set cover, right. If you can get provably something an approximation factor better than log n, right, then it means that this problem is actually easier to some extent than the generic set cover problem.
So the vertex cover or edge cover is to approximate solutions are.
But that is a very special case of a set cover, right. This is a vertex cover is a so set cover. The generic set cover problem has a log n solution, and that is also a lower bound. But vertex cover is a special case of a set cover problem, which is also a hard problem, but is a factor 2 approximation. Right. So, this is also the sets are given to us, the elements and their sets. Okay. The only difference between the generic set cover and this is that this has a bounded VC dimension. So, yes, I mean to some extent what you are saying is right. I mean we can relate, if we can relate to the fact that vertex cover has a better approximation factor because it is a special case of a set cover. This is also a special case of a set cover problem because it has a bounded VC dimension. So, we want to see if we can do anything with anything better than the generic set cover because we have a bounded VC dimension.
And the set cover also has a factor F approximation where if the maximum number.
No, so we are not imposing. Yeah, sure. Yeah, so there are all kinds of these special cases where you have things. So, this can be viewed upon as a special case, but this special case is rather, it is still quite generic because it manages to cover the whole domain of geometric configuration and many other things. Right. So, this is a very one of the most relaxed sort of version of the set cover, where we are hoping to get a solution provably better than what we get for the set cover. This still contains a large number of naturally occurring problems in the geometric domain. Okay, so the answer to this is clearly yes, because we have been building up to it. So, how should we go about this? Okay. So, before I present the algorithm, let me go back to the definition of the epsilon net, okay, because that we will require for the algorithm. Okay. So, I did give an intuitive definition of epsilon net, that it is essentially some kind of a cover for large sets. Epsilon net essentially a set cover that covers only the large sets. Right. So, here is a formal definition. Okay, so let me remind you that m sub x is all the so let me not define this is sorry just one moment, just let us only use this. So, m sub r is the ratio of the points lying inside the range of the sample divided by total size of the sample. Maybe I should write this. Yeah, that's fine. Okay. Yeah, right. Okay. So, this is the so there is some range R, okay, that contains at least epsilon fraction of the points. It's a relatively large range. Okay. So, number of points of x inside this range R divided by the total number of points. Okay. This I am saying is greater than or equal to epsilon. So, this range is a fairly heavy range. It contains a lot of points of x. So, moment we have such a range that then we require that this subset n must hit at least one point of this range.
What is capital X here?
Capital X is okay, the range space. Okay, so the range space is Oh, sorry. I shouldn't use capital X. I'm using small x. So range space is x comma r. So capital X is some subset of n points.
Sir, in the second sentence of definition, it must be then n contains at least one point of r.
Yes, capital N contains.
N contains at least one point of
R for all the subsets r.
R intersection X. No. So what am I saying? Oh, sorry. I am N contains. Finally, I think got it right. Sorry. Okay, so let me go through it again. So a subset N is an epsilon net for X if for any range that contains a large fraction of the points of X, okay, N must contain at least one such point. Okay. So, how does one construct an epsilon net? So, turns out that the easiest way of computing an epsilon net is that you do some random sampling. Okay, you select a sample of a certain size, and you can prove that if you choose a large enough sample, okay, it will satisfy this property, which in some sense gives an existential proof that there is an epsilon net of this size. See, if I choose all the points, okay, of course I am going to hit everything. Okay. The point is that how small can I make this subset n? How can I choose this capital N as small as possible and still accomplish this thing? Right? I am trying to hit everything, so I want to find a small hitting set in some sense. Right? It has to hit all the large subsets. Right? So if I pick up all the points, of course, that's a trivial solution, but I'm not satisfied with that. So we want to select relatively small subset n, okay, and if we pick this subset by random sampling, and I pick a sample of certain size that I will just state, what those bounds are, and we show that that is an epsilon net with a non-zero probability, there is some positive probability. It means that there must be some subset of that size, okay, which fulfills the condition of being an epsilon net. Okay. So, it is an existential proof. So, it is a so that sampling is a randomized algorithm because it is an algorithm. I just have to sample, okay, and the samples satisfy that property. That is constructive. Okay. But if someone is interested to find out such a subset deterministically, okay, then that is a different ballgame. Okay. So, all you know is that if I pick a subset of this size, okay, randomly, then it satisfies the property. Now, what do we have to do so that we can choose that subset deterministically? Okay, that would be the other challenging problem. Right? And it turns out that if I suppose I manage to show, let us say there is some, if I pick 100 points, okay, then it's a epsilon net with probability at least half. Okay, then from that argument, that existential argument, one can use something called general de-randomization techniques. Okay, so there is some technique by which you can de-randomize certain algorithms, not all algorithms, but it so happens that for epsilon nets, okay, and well, actually not just epsilon net, something called epsilon sample. Okay. So, here what are we doing? We are saying that this one, as long as is a large subset, okay, we will pick up at least one point of this. Okay. In the epsilon, we, I do not know if you recollect the definition of an epsilon sample, we want that ratio. Okay. So, the number of points that I pick up from this subset, okay, here we are saying 1 is sufficient. Okay. But if we require that ratio should not be the ratio when we are talking about points in n and the ratio when you are talking about the points in x, they are not very different. Okay. If we want that to be very close to each other, okay, suppose I want this condition, okay, let me write it down. Suppose I want this condition that n intersection r, okay, divided by n, okay, this is the number of sample hitting that range r, okay, minus the number of points in x that intersects that and the ratio, okay, this one. So, if I want this ratio to be bounded, okay, let us say I want this whole thing, take the absolute value of that, okay, and suppose I can bound this by some epsilon. I did not have room to the right, so I will just write it here. So, suppose this is less than some pre-specified epsilon, let me use maybe something else phi, okay. And this will again hold only for the large subsets. So, we are saying that this will hold only for m's of r greater than epsilon. Okay. Again for the large subsets, okay, I want this condition to hold and such that the difference between these two ratios is no more than some pre-specified phi. Okay. So, this is a more stringent condition. It is not just one point that I want even that the difference, the ratio to be bounded. Okay. Then it is called an epsilon sample. Right. So, there is a way that you can, so this random sample, you know, gives us some properties of an epsilon sample, and from there it is possible to de-randomize, okay, to get a epsilon sample of, let us say, a size which is no more than the constant times what I get by randomized arguments. Okay, suppose my randomized argument shows that if I pick 100 points it is sufficient, then starting from that point, that existential proof, okay, we can convert that, you know, using some very clever searching methods in polynomial time, okay, to obtain a deterministic sample, let us say deterministic sample of size, let us say no more than 2 times 100. Okay. So, that those are generic techniques that are called de-randomization. Okay. So, it is possible to de-randomize some of these algorithms, this epsilon net finding algorithm, to actually construct an epsilon net deterministically of almost the same bound as what you get by randomization. Okay. But this is rather neat and simple. So, we will not get into that, that will require completely different techniques. You know. So, I will just state the bounds, you know, what is the sample size that you require, that will guarantee that. Okay. It is not a lower bound, it is an upper bound. Okay. So, this is the bound essentially. It's a little messy expression, but it has fallen out for some kind of proof. So, what are we doing? We have this finite set of points small x. Right? We are creating a random sample by sampling each point of x, okay, uniformly. So, I'll create a sample, if I have 100 points, I want to choose 50 points. What I am going to do is I will choose one point at random, okay, and then I will choose the next point at random, and so on and so forth. So, independent draws essentially means that these are so I have a little bit of doubt whether it should be with replacement or without replacement. Let us say this is without replacement. Okay, so I draw one point. Okay, then I draw another point, and so on and so forth. Okay, so I create this random sample of this size m, small m, and small m is larger of these two terms. What is the significance? So we have a bounded VC dimension delta. Okay, so this sample size turns out to be a function of the VC dimension delta. You can see there is an 8 in the second term, there is an 8 delta. Okay, and there is also it must be a function of epsilon, because we are constructing an epsilon net. So, it must hit all sets of size at least epsilon n, right. So, it is a function of both epsilon and delta. So, the larger the VC dimension, the more points we need in the sample. The smaller the epsilon, the more points we need. Okay, that is how we can reconcile these two. And then there is a dependence on phi, okay, which is nothing but the success probability. Okay. So, if you can choose phi to be equal to half, let us say. Okay. So, we are satisfied as long as there is a positive probability that it is going to be an epsilon net. Okay. So, if you can set phi to be equal to half, and then then you may not even want phi in the expression, but this one says actually it is a very general expression. If I want a higher probability, then of course phi is the failure probability, so it is inversely proportional to phi. Okay. So, this calculation, okay, requires a proof, okay, but we are not going to go through this proof. This proof is not that hard, but the proof uses one very clever observation which will require some time for us to digest. Now, what I can do is I can post this proof, or I can make a Xerox copy of this and leave somewhere, so you can access that. In fact, I could do the same thing with the lectures that I have been doing the last few weeks. So, it is from an unpublished manuscript. Okay, so I can't make it public, I can't post it on the web, but I have the author's permission that I can sort of make the printed copies available to you. Okay. So, I will do that. It is about 70-80 pages of okay, it is not very trivial. Okay. But anyway, so I will leave it so that if someone is interested in the proof of this proof is available in many places. If you just search the internet, you will find a proof of the VC dimension. The proof is not trivial, but the proof is not too hard. It is along the same lines that we have been arguing before, but it requires one clever trick. Okay. So, that I do not want to, that is why I get into this today. This was given by the original paper, Wapnik-Chevronen case. So, the original paper contained this bound actually. So, the object of the original paper was to show that there is an epsilon net of this size, right? And the de-randomization etc. has been done much later. So, this was in the early 70s, de-randomization happened sometime in the late 80s. That is the de-randomization is due to Matuszek, Jirka Matuszek. Okay, so just stare at this, and then we will take off into the algorithm. Okay, so there is, let us say, some bound that if you pick a sample of this size, then it is going to be a epsilon net with some, let us say, probability at least half. Okay. In other words, and suppose I can verify this. Okay, suppose I can verify that whether or not a sample is a epsilon net, and if I do not succeed, what do? I resample again. So, if it succeeds with probability half, then in the expectation I need to only resample twice before I actually get an epsilon net. Okay. This is the way so this is a randomized algorithm, it will work by repetition. Okay. Yeah.
So, the size of epsilon net is small m or capital N? Confused between m and.
No, the capital N is the subset that is constructed, and m is the small m is the size of the sample. So, have I used, so n be a subset obtained by n independent draws, right. So, size of m is n, right. I am constructing the sample this way. So, as long as it is larger than this size, as long as the sample is larger than this size, then it satisfies the property of a epsilon net. Right. There is one more comment let me make. So, here we are talking about VC dimension. So, yeah.
So, what is the importance of choosing small x to be a finite subset of capital X? You can directly use that capital X and choose randomly as.
No, capital X may or may not be finite, right. Capital X could be just space of the plane basically, or the real line or whatever. So, the definition of VC dimension as such does not is not limited to finite spaces, it applies to Euclidean spaces or other continuous spaces, but when you are defining, so that is one of the beauty of it actually. So, we are defining it for a continuous space, okay, but the definition is with respect of the shattering function is with respect to a finite point set. So, the definition of the VC dimension is with respect to a finite point set, okay, and then the shattering function, okay, the shattering set, and so somehow this continuous space can be captured by some finite point set essentially. Okay, so one more comment on this is, if instead of VC dimension, so here we are using in the formula VC dimension delta, right. Suppose instead of VC dimension we were given the shattering dimension. Okay. Suppose we use the shattering dimension of S, say D. Okay. Then again we can get some kind of there is a relationship between shattering dimension and VC dimension. Okay. So, we could write a formula, and if you simplify that, it turns out the sample size can be relatively that formula is relatively simple. So, then sample size is greater than or equal to I think it is order delta over, sorry, d over epsilon log of. Okay. So, here d is the shattering dimension. So, if you use the shattering dimension instead of the VC dimension, then the size of the sample turns out to be about this much. Right. Okay. Now, we go to the algorithm. So, maybe I should make one more comment on this before I go to the algorithm. So, this is an epsilon net, the formula for epsilon net when the elements are unweighted. Okay. Suppose, just make this comment, another comment basically. Suppose the elements of x are weighted, i.e., there is a weight function some real numbers. Okay. And the weight of a subset of R, okay, equals the weight of summation of over all x, weight of x okay. So, in this weighted scenario, so here we were interested to hit every large subset in terms of cardinality. In the weighted scenario, we will be interested to hit those ranges that have a certain minimum weight associated with it. Again, maybe, so if capital W is the total weight, okay, suppose I am using the x in too many ways. So, the sum of the weights of all the elements in X. Right. Then we may be interested to hit the large weighted ranges, okay, namely those whose weights are epsilon times W. So, I would like to hit those ranges that have weights greater than at least an epsilon fraction of that. Right. Then again the same sampling theorem works. Okay. A similar result can be proved, okay, where the ordinary sampling is replaced with weighted sampling. What is the weighted sampling? If the weight of a particular element is larger, then the probability of choosing that is more. So, we normalize with respect to the weights, and that is the probability of sampling. Okay. And how do you do this kind of weighted sampling? You know, one simple way to do weighted sampling is that suppose I can do uniform sampling. Okay. In this, so I take the interval, okay, and suppose I have different, I want to sample elements of different weights, okay, then you just have those, you know, intervals of different weights, okay, and then when you sample uniformly in this interval, then the chance of picking an element from a larger interval subinterval is more. Okay. So, this is the simplest way of doing a weighted sampling. So, you can do weighted sampling also fairly easily. Okay. So, now let us proceed to the algorithm. So, what does the algorithm do? It repeatedly selects an epsilon net for some epsilon. Okay. I have not defined what that epsilon is going to be. What is the problem? The problem is that we have this is the setting, right. We have a set of n points, we have a set of m ranges, and we want to pick a subset of the ranges such that all points are covered. So, what are we going to what are we choosing? We are actually choosing the ranges, right. So, we are sampling actually from not the range space, but the dual range space, right. We are not selecting the points, we are selecting the ranges. We want to choose the ranges. So, although the problem is posed in terms of S, okay, we are actually going to choose the subsets or choose the sampling in S star. Okay. Of S star. So, this epsilon net will be chosen from S star. Now, because S has a bounded VC dimension, S star also has a bounded VC dimension, all those things. So, we will assume actually S star, suppose has S star has a so I will use the shattering dimension, because the sample size is more easily expressed with shattering dimension. Okay. So, suppose this is shattering dimension. Once that has a bounded VC dimension, everything is bounded. That is what we observed yesterday. So, suppose the shattering dimension of the dual range space is delta star. Okay. So, what kind of epsilon are we going to choose? Okay. So, the algorithm is the following. Okay. It's a very simple algorithm. And it can be useful in many other contexts. So, I choose some epsilon sample where epsilon I have not defined yet, what the value, we will do some back calculation to find out what the epsilon should be. I choose an epsilon sample and then I verify whether or not this is a cover. Okay. If I choose a sample of a certain size, okay, it is going to be an epsilon net with, let us say, probability at least half. Okay. If it turns out that it is not an epsilon net, we will discard that sample, we will not do anything with it. Right. If it is an epsilon sample, okay, we will first figure out if all the points are covered. We are sampling what? We are sampling the ranges. So, we just will check actually if all the n points are covered by the epsilon net that we have by random sampling. Okay. So, the epsilon net was considered by random sampling, but we just actually, let us say, brute force check if every point is actually covered by that epsilon net. Now, if it is covered, then we have a cover, okay, and the cover will be of the size of the epsilon net. So, we output that cover, right. So, let me see what I am saying. So, choose an epsilon net, and let me point out that it will be weighted. Okay, we will see why it is weighted. Initially, all weights are 1. Okay. So, what is the formula for the sample size? It is delta star over epsilon log of delta star over epsilon. Okay. So, this is choose an epsilon net weighted of size r, call it, let us say, some y. So, we have chosen y, okay. We have chosen it by random sampling. Okay. We verify first of all if y is an epsilon net. Okay. If not, discard. So, I am not even interested if it is not an epsilon net. Now, if it is so, if else okay, then we check if y is a cover, and this cover you check just by brute force. Okay. Whatever time it takes, there are n points, and this is a cover size, and suppose I can do the test in constant time or something, it will take some n times the size of the epsilon net, right? Brute force. Or if you have some clever method, use that, feel free. So, if it is a cover, okay. So, if it is a cover, okay, if it is a cover, then output y. How good a cover, how good a size, so what kind of size y has, we know this is this size. So, basically we now get something of the size of this epsilon net, that is the size of my cover. And see, this one does not have anything other than the property of the range space, right. Delta star is the property of the range space, okay, and epsilon is what we have not defined yet. So, I will define epsilon also, okay. But this is free of those n, there is no dependence on n really, okay. It only depends on the property of the range space, although I have not defined epsilon yet, okay. Epsilon will have some kind of dependence on the size of the optimal set, okay. We will soon get to that. So, then output y and you are done, okay. Else if it is not a cover, what do we do, okay. Then there must be at least one point P in X that is not covered. There is at least one point that is not covered. Now, what we do is you look at all those ranges, let R P is equal to all those ranges, okay, such that P belongs to R, right. So, if I had chosen even one of these ranges, the point would have been covered, but we have not chosen anything, otherwise there was no problem with this. There was, I mean, we would have output y as a set cover. So, there is so some point P is uncovered and we are defining the corresponding R's of P, and there must be also observe that one of the so if so note that R P must include some range R prime in the optimum solution also, because the optimal solution must cover every point, right. So, there must be some range R prime, okay, that must be in R P. Okay. Why I am saying that? This is not a part of the algorithm, I am just bringing something to your notice. Now, what we want to do? We have missed out this point P, okay, and we do not want to do anything else but just resample, we will try another sample next time, but then next time also we may miss P or maybe we will miss something else. Okay. So, what do we do? Exactly, great. So, what we will do is basically just increase the weight of all the ranges in R sub P, which includes R prime also, right. So, there is some unknown optimum set cover, okay, which we do not know, but when we increase this weight, okay, we will double the weight of elements in R P. Okay. So, we will double these weights. Okay. There is a subtle condition here. Okay. Let me say what it is. If weight of R p is less than, strictly less than, let us say, epsilon w. Can you tell me why I have put down this? So, intuitively we are increasing the weight of all the ranges in R p, with that includes R prime also. Okay. So, next time we do a random sample, we miss some point, again some subset of this optimal cover, the weight will double. Okay. So, every time we do not get a cover, we are going to increase double the weight of some range in the optimum cover. Okay. And if we keep doing it many times, okay, the optimum cover, okay, is increasing its weight, okay, and it is going to increase its weight very rapidly. Okay. So, at some point, okay, we should be able to basically get, we should be able to get a cover, that is the point, okay, and the cover is of the size of the epsilon net. So, we repeatedly do this, okay, by reweighting, okay, but I have also added this condition. Can you tell me why?
Because you want to reach the large weighted ranges.
No, see, we have retained this epsilon net y, okay, only if it is a, yeah, only if it is epsilon. Well, we have retained the subset y only if it's an epsilon net, right? So, if it is an epsilon net, then it is supposed to hit all subsets of which has weight at least epsilon times w. Okay. Now, if R p had weight epsilon times w, it would have hit it. Okay. Then there would not have been any need for it. Okay. So, if we are assuming that the sample that we are retaining is an epsilon net, y is an epsilon net, then the weight of that must clearly be less than epsilon times w. Okay. So, observation, every time we double the weight, we are increasing the weight by no more than so this is one kind of bound that we have basically, so a factor of 1 plus epsilon. I think I will have to probably wind up here. Okay. Right. This weight is being doubled, right. This weight is being doubled only when the so because it is an epsilon net, the weight of this subset is no more than epsilon w. Okay. So, when we double it, it means that we are increasing the total weight of the entire system by no more than epsilon w, which means the total weight is not increasing more than 1 plus epsilon times what the previous weight was, right. The weight of this subset is less than epsilon w. Okay. I am doubling it. It means that I am increasing the total weight of the system by epsilon w, which means that if you compare w I at the ith time that I double, okay, is less than or equal to 1 plus epsilon times w I minus 1. That is all you are saying. Okay. So, here is where I will end today. So, if therefore, w I is less than or equal to 1 plus epsilon times w I minus 1, which is basically saying that the same thing as w I is less than or equal to 1 plus epsilon times to the power I of m, that is nothing but w 0. Okay. So, this is one kind of bound. Okay. This is one kind of bound. So, I, by the way, is in iteration where weights are doubled, i.e., that it is actually one of those iterations which where we successfully picked an epsilon net. Okay. If we do not pick it, then we forget about it. And because we are succeeding with a fairly high probability, about 50% of the times. Okay. So, eventually when we count how many iterations do we need to pick a set cover of this size, okay, we will have to kind of double this in the expectation, because in half of those iterations we are successful anyways. Okay. So, we are only counting the number of iterations where we double the weight. That will simplify the analysis, and the total number of iterations will not be more than 2 times that in the expectation. Okay. So, tomorrow I will complete the analysis. So, this is one way of bounding the weight. The other way of bounding the weight will be just looking at the optimum subset. Okay. The optimum subset has at least one subset where the weight is doubling. Okay. And because the weights are doubling in that subset, it can't go on for too long. Okay. And we will find a lower bound of the weight picked up by that subset. Okay. So, then we will be able to just equate that this weight must be greater than or equal to that weight, and that will give me the bound on I. Okay. So, we will end here today.